Okay, so welcome everyone to our usual Wednesday at EP seminar. And today we are delighted to have Olga Papadoulaki from the École polytechnique, who will tell us about the recent progress on Euclidean wormholes and their holographic duals.
Thank you very much for the invitation and the introduction. My talk today is based in various papers that I have in collaboration with Panos Begios, who is a postdoc at the University of Ghent, and two of those are also in collaboration with Elias Kiritsis, who is a professor at Crete and Paris, as well as my most recent work with Panos Begios again, Jikun Lee, who is a postdoc at ETH, and Yan Zunzu, who was my master's student here in Polytechnique, and he will start his PhD next year at Berkeley. So let me start with some introduction, why we are interested to study Euclidean wormholes. So wormholes are interesting exotic solutions of gravity plus matter, and they have various physical effects. For example, they lead to a non-trivial topology of space-time. They connect the black hole interior with its exterior, and they have implications on the information paradox. And upon analytic continuation, they are related to cosmological spacetimes. There are various types of wormholes. There are Lorentzians, where one of the dimensions is time. There are Euclidean. They can be macroscopic and saddles, so they can connect different asymptotic regions, or they could be microscopic and form a gas of wormholes that they connect to the same asymptotic region. These two exist in different scales. So macroscopic ones is when their characteristic scale is of the order of ADS and much larger than the Planck length. Whereas microscopic, they are when their length, the characteristic length is bigger than L Planck, but much smaller than LADS. In this talk, the main focus will be macroscopic Euclidean wormholes in the context of holography, and the plan of the talk is the following. I will give an introduction, then I will present what we can learn from the bulk side, and based on that, I will propose some dual QFT models. And I will finish with a specific example where we have bubbling wormholes in type 2b that are dual to backreacting Wilson loops in n equals 4. And I will have some summary and some future directions. So let's start with the introduction. So let me just very briefly mention Lorentzian wormholes, since these are the most well-known. So the most well-known one is the Einstein-Rosen bridge that connects the left and the right exterior of the eternal black hole in ABS. And this is dual to an Einstein-Podolsky-Rosen pair of two disconnected black holes that they are in a very particular entangled state. And if we are in EDS, we have holography, so at the boundaries there are two CFTs that live, and their energy levels are correlated in this fashion. And essentially this tells us that large amounts of entanglement can give rise to a geometric connection. So in holography, we interpret such a geometry as describing a pair of entangled but decoupled holographic UFTs, and we cannot communicate a message between the two sides through the wormhole. The two boundaries are always separated by a horizon once the null energy condition is assumed for the gravitational theory. And upon analytic continuation to Euclidean signature, the space smoothly closes, creating two disconnected Euclidean cigars. One can also create traversable wormholes. These are Lorentzian signature solutions for which the null energy condition is violated. In this case, a signal can pass through the wormhole. This can be done holographically by introducing a double trace type of interaction of this form with an operator in the CFT left and the CFT right, so essentially by coupling the two quantum field theories. So I will pass now to Euclidean wormholes, which is what we will discuss here. So in Euclidean wormholes, we only have Euclidean space, there is no time. And to have such solution, one needs to have locally negative Euclidean energy in order for the throat to open up. Such energy can be provided by appropriate matter, for example, if we have axionic fields or magnetic fluxes. And indeed, there are several such solutions in different dimensions and setups, and some can be embedded in the standard model plus gravity, and the subset of those can be shown that is at least perturbatively stable. Now, there are other reasons why we are interested in Euclidean wormholes. So generically, Euclidean geometries have interesting connections upon analytic continuation with Lorentzian ones. And essentially, we can use them to slice them and prepare the state or the wave function for the Lorentzian evolution. For example, the sphere corresponds to the Hartley-Hawking wave function, so the no-boundary state for cosmology. We saw that the Euclidean cigar corresponds to the thermophile double state for the eternal black hole. Now, Euclidean wormholes, they are not related to black holes, to solutions with horizons by analytic continuation, but instead, if we choose to analytically continue the radial direction, we get a background cosmology, whereas if we choose to analytically continue one of the transverse direction, we get reversible wormholes, but such continuations could lead to pathological saddles. For example, maybe the background fields could become complex. Now, since we don't have, we talk about Euclidean wormholes, there is no time, there is no obvious notion of entanglement, as in the case for Lorentzian wormholes. And since we have two disconnected boundaries, we can have global symmetries there that seems to be completely dependent. But holographically, these come from the same bulk gauge field, and they should satisfy the same Gauss flow constraint that essentially relates them. And what this leads to is that the symmetries are broken to their diagonal subpart. One can insert operators to compute correlators, and we can have two types of correlators. One can insert have insertions at the same boundary, or which is what we usually have when we have one asymptotic region, but we can also have insertions, one insertion to the boundary one and one to the other, and we can have cross correlators. And we can find that this type of correlations, the cross correlations, don't have short distance singularities. One might have expected, since we have two disconnected Euclidean quantum theories at the boundaries, the cross correlator to be zero and the Zwinger fractional to be the product of the Zwinger fractional of theory 1 and theory 2, so to factorize. But if we take into account the bulk picture, we see that we do have some form of cross correlation, and this gives rise to some weird properties that we want to understand better. So this is a so-called factorization problem, where, as I already mentioned, if we had only this picture that is just the two asymptotic regions where the two CFTs live, we would expect cross correlators to factorize. But from the bulk, we can have configuration like this that connects them, and indeed we do find such correlations. Now, there are various proposals in the literature for how we can resolve this puzzle. The most the most standard one is that we should interpret the quantum gravity path integral as corresponding to an average. But what this average means is different. There are different options. So one idea is that we have explicit averaging over an ensemble of quantum field theories. And this is the example of JT gravity that is dual to S2K, where we integrate over all possible couplings, or dual to the matrix, to the Gaussian matrix model. But in this case, where we average over random Hamiltonians, but in this case, the theory is not unitary anymore. And this is something we observe in lower dimensional theories of gravity, where gravitons are not dynamical, so they have quite different properties than the canonical example of gravity in 4 dimensions and higher. Also, this type of interpretation is very different from the canonical example of ADCFT, where we have a single theory with fixed parameters. So we have ADS5 cross S5 that corresponds to an equals force per Young-Mills, and all parameters are fixed, and we don't have any free parameter to average over. And one geometry corresponds to one quantum field theory. One can interpret this averaging as the statistical approximate averaging. What this means is that when we write the gravitational path integral, essentially we work in the semi-classical limit, in the semi-classical gravity. And of course, we cannot see all the details of the UV theory from that computation. So essentially, effectively, what we do is that we have integrate over the UV quantities we cannot access, and this is why we see these geometric connections. And if we had, and this type of averaging, and if we had access to the whole UV complete theory, we wouldn't see such a thing. And this is consistent with n equals for planar integrability, because this type of observables show up above the black hole threshold when we have chaos, chaotic behavior in black holes. And this type.
Can I ask a question?
Yes.
So what is your selection criteria? Which saddle point solutions you can include into the calculation of gravitational path integral? Which wormholes are kind of correct saddle point solutions and which are not? Or you just take them all?
Well, here, okay, what I will discuss is the geometry is going to be semi-classical. I'm not going to perform a path integral and select saddles. But generically here, they don't have to be saddles. You can, they don't have to be solutions to the equations of motion.
You will find wormholes as a solutions, right? Of gravitational equations.
Yes.
So
Yes, is what I will describe.
and your motivation is that if you calculate some correlators between different ADS boundaries, then these saddle point solutions will give contributions into the gravitational path integral, right? Or I misunderstood.
Is one of the motivations, but not the only one.
Yeah, but in gravity, there is a problem sometimes that you have some, for example, solutions which have negative action, and formally they correspond to probability which is exponentially large, or some other crazy solutions which you
Right.
simply shouldn't include. So, what is your answer to this?
So you
Yeah.
can, okay, I'm not going to discuss this in this talk, but you can find wormhole solutions. So the ADS asymptotics helps you with having a well-defined probability upon, of course, holographic normalization. So you don't have, for example, the issue that you have with the Hartle-Hawking proposal, where the probability is extremely large because the on-cell action is negative, and of course when you have you are in the WKB approximation, so you have e to the minus s for the probability, whereas s is the Euclidean on-cell action, and this becomes huge. So essentially the ADS asymptotics helps you with that problem.
So basically, in ADS, and you say that any solution will do because they kind of give reasonable results.
Yes.
Oh, okay. Another question is, are these wormholes somehow connected to some maybe replica wormholes, or these are absolutely different solutions?
No, these are different.
Okay.
Okay. Uh, So a different resolution that I will propose here is the following. So we will have some interaction between the two CFTs that has, as we will see, very specific form. It should be soft in the UV and strong in the IR. And this could lead in a Zwinger functional of this form, where we have the Zwinger functional of theory 1 times the Zwinger functional of theory 2. Some appropriate weighting function, and we sum over this parameter S, some sector, which this is dependent of the example. I will discuss this later. And this type of Zwinger functional is reflection positive. So the theory would still be unitary. And this type of theory would give the feature of the cross-correlator that we mentioned, that the cross-correlators are averages of lower point correlators of the two individual subsystems, and the cross-correlators, they don't have singularities. So let me briefly mention the bulk perspective. Okay. So, as I mentioned briefly also in the beginning, we can find various types of asymptotically ADS wormhole solutions. So essentially, pictorially look like this. We have two ADS asymptotic boundaries connected with a throat. In our papers, we analyzed various examples in different dimensions, 2, 3, and 4, and with different matter content. The important thing is to have some form of negative Euclidean energy to support the throat. And this can be done either by having action fields or having electromagnetic radiation where the magnetic part is dominant. Or you could slice your transverse space with hyperbolic slicing. So you have a negative curvature there. So once you have the solutions, I will not show the details here, we want to understand their properties. So to do this, we want to study further observables. So the simplest thing we can do is to study correlators of local boundary operators. Here we studied scalar operators. We call them O1, O2. This holographic corresponds to studying the second order bulk fluctuation equation for the dual scalar field. And since we have two asymptotic boundaries, we can insert operator sources, either in both of them to be in the boundary 1 or boundary 2. This we call O1, O1 or O2, O2, or we can have cross correlators with O1 in one boundary and O2 at the other. And indeed, what we found is the following. So these are the plots of the correlators. This is the 1-1 correlator, and this is the cross correlator as a function of momentum. This is for the case of global ADS2, which is a wormhole. So we see that when we have insertions at the same boundary, we have similar UV behavior as when we have one asymptotic boundary, so we have a parallel divergence. And in the IR, they saturate to a constant positive value. Whereas for the cross correlator, we see that it goes to zero at the UV and has a finite maximum in the IR. So the expressions in the position space for the correlator with insertions at the same boundary are 1 over sin to the 2 delta plus, whereas for the cross correlator is 1 over cos to the 2 delta plus. So from this form, it's evident that we don't have short distance singularities. Now, what we observed was that the same qualitative behavior persisted in solutions to higher dimensions and with different matter content. So the holographic dual of wormholes definitely have these features. Now, apart from local observables, we also studied non-local observables, such as expectation values of Wilson loops and Wilson loop operators. So also, if we study Wilson loop observables, we can refine the analysis of Slenker and Witten, which they studied the compressibility of appropriate boundary cycles in the wormhole bulk. Now, if we want to study the expectation value of a Wilson loop holographically, we have to find the string Walsh that tends on the corresponding loop C on the boundary, if it exists, and minimize its area. So the simplest observable is to have a single Wilson loop insertion and compute its expectation value. And again, we found the universal features that large loops on the boundary penetrate further in the bulk, and we can probe the IR properties of the dual boundary theory. And typically, we find an area low behavior in the IR. Now, imagine that we also had a non-contractible thermal cycle, S1. Then there is no bulk surface that can end on this, and its expectation value is 0, which is reminiscent of some kind of confining behavior. So the center symmetry is preserved, which is in contrast with the case of the black hole cigar, where the expectation value is non-zero and we're in the deconfined phase. Now, we can also study loop-loop correlators, where we have one loop at the one boundary and one at the other. We observe that as we shrink the boundary loop, we find that the leading configuration of Lowe's taxon is the one of two disconnected loops that interact with perturbative exchange of gravitons. Whereas in the regime of large Wilson loops, the leading contribution comes from a single surface that connects the two loops and having a cylinder topology. The larger the loops, we see stronger IR cross-coupling. Now, imagine again that we have a non-contractible thermal cycle. In this case, we find only a connected cylindrical bulk surface with non-zero expectation value, which is consistent with the fact that the wormhole essentially breaks the boundary symmetries to their diagonal part. But the diagonal center symmetry stays unbroken, and we term this as a cross-confining behavior. Now, based on this, we can propose a dual picture, a holographic picture. So imagine we have the following tripartite system. So we have two d-dimensional holographic boundary quantum field theories on a manifold sigma, coupled through a d+1 intermediate messenger theory on an interval cross sigma. This messenger theory has a much smaller central charge. It is not holographic. And we would like the system to flow to a gapped or confining phase in the IR. The geometric idea is that the dual bulk gravity can localize on d+1 dimensional end of the world branes that bend and connect in the IR. Here we focus in the case where the messenger theory is quasi-topological, so there is no contamination from d+2 bulk perturbative modes coming from the intermediate theory, and we have a natural gap in the IR. Upon integrating out this topological quantum field theory, the messenger theory, we will get a Zwinger functional of this form we advertised in the beginning. Now we can analyze a toy model of this form, where we have the messenger theory to be a two-dimensional generalized Young-Mills. So here is the action. And we couple it to two one-dimensional UN-gauged matrix quantum mechanics theories with Hermitian matrices M1 and M2 that lives at the endpoints of the interval. And this covariant derivative is with respect to the boundary value of the gauge field coming from the generalized Young-Mills. We analyze the solvable example where the potential here is B squared, and essentially we just have 2D Young-Mills coupled with two Gaussian matrix quantum mechanics models. So now we place the system in an interval cross S1, so on a cylinder of length 2L and circumference β. And the 2D Young-Mill amplitude on the cylinder can be written in this form and depends on the two asymptotic holonomies U1, 2, which are the zero modes of the gauge field. Here are the representations of the U-engaged group, and 0, 2, and 1 are its Casimirs, and chi r are the characters of the UN, which are the wave functions at the end of the cylinder. From in the matrix model system, we integrate out the Gaussian matrices, the Hermitian matrices, to obtain the matrix quantum mechanics partition function of this form. And we couple the 2D Yang-Mills amplitude to the two matrix quantum mechanics partition functions and integrate over the zero modes. And then the complete expression on the cylinder has this form, where beta is the S1 size and HR here are and HR is the Hilbert space of HR here is the Hilbert space of the matrix quantum mechanics in a fixed representation R. Essentially, so we see that this acquires the form that we advertised, and essentially the two matrix quantum mechanics representations are correlated or entangled, and the summation over the representations, we would see it as a form of averaging that is consistent with unitarity or reflection positivity for a single tripartite quantum mechanical system. So this representation is what in the beginning I called the sector S. So here we didn't do any approximations such as some form of cross-graining or some eigenstate thermalization hypothesis or averaging over different theories. And the allowed representation in representation with sum are center symmetric. So indeed, we broke the two gates group to its diagonal subgroup with this capping. Now, I will pass to the case of n equals 4 Wilson loops and type 2B bubbling wormholes. So one can see this 2D, 1D model I described as reminiscent of SUSY localization computations of line defect operators in n equals 4 super Yang-Mills. And the idea we have here is to correlate representations of 1/2 BPS Wilson loops in higher dimensional examples that have known semi-classical holographic duals. So here specifically we consider two non-interactive copies of n equals 4 super Yang-Mills and a correlated observable of this form where WR are 1/2 BPS Wilson loops in some representation R. Now, a single half BPS Wilson loop in the representation R is computed via localization. It was done this by Bestun and results in a Hermitian matrix model of this form. And we would like to understand the limit where the operator is very heavy and backreacts strongly in the dual geometry. Now, representations that they have ON boxes are still light. These are correspond to the branes. So we need to consider representations R with ON square boxes and the highest weights I to be order N. The Young diagram of such representation is described by a collection of rectangular blocks, each with ON square boxes and size Ni and Ki. Ni are the number of rows and Ki the number of columns. And once we project this to the real line, we acquire a diagram which consists of black and white lines. And the black lines corresponds to the cuts of the matrix model resolvent, which in turn we see dictates the form and the properties of the dual supergravity solution. Now let's discuss the specific solutions. So the geometry dual to a backreacted loop in a representation R has an SO 2,1 cross SO 3 cross SO 5 isometry. And the metric has this form. So it has an EDS2, an S2, and an S4 factor, and the Riemann surface sigma. And all the metric functions and the rho depends on the coordinates of the Riemann surface sigma. The Wilson loop lives on the S1 boundary of the ADS2 disk. And the solution, in principle, can contain non-trivial dilaton and 3 cycles, 5 cycles, and 7 cycles, with RRR and SNS fluxes supporting them. Now, everything is determined by two harmonic functions. So when H1 and H2, the zeros of H2 determine the boundary of the Riemann surface sigma, and H1 contains the data of the bubbling geometry. So the cuts of H1 correspond to fluxes, and the singularity corresponds to asymptotic in this 5 crosses 5 region. And the matrix model resolvent has a classical part and a quantum part, that is the spectral curve, completely determines H2 and H1, the two harmonic functions, so completely determines the dual supergravity solution. So this here is when we have one this 5 crosses 5 asymptotic region and one backreacting Wilson loop. Now, we can obtain solutions with more singularities, which means with more ADS 5 crosses 5 regions, that we still preserve the regularity conditions by Docker-Estes-Sergi pair, which are the following: that H1 may vanish only on the segment of the boundary of the Riemann surface, where the S4 vanish, so only off the branch cuts. We see it here. The segments of the boundary of sigma, where H1 is different than 0, correspond to the vanishing of the S2, which is here. And H1 and H2 are positive definite in the interior of sigma, but can vanish on their boundary. So the additional condition we should impose in order to be able to have more than one asymptotic ADS 5 crosses 5 region is that H1, 2, so the harmonic functions, need to have common singularities on the boundary of the Riemann surface sigma. Now, the simplest such Riemann surface corresponds to a disk with two cuts and two singularities, and we can imagine that this sigma is the lower half plane. And this symbol here symbolizes a conical excess that I will discuss a bit in a couple of slides further. Now, let me discuss the features of these bubbling wormhole solutions. So the geometry has a Euclidean ADS2 factor with this topology, and its boundary S1 is shared by all ADS5 asymptotic boundaries. So this means that the would-be distinct S4 boundaries of ADS5 are identified at a common S1 in analogy with other Janus type of solutions. So these are not really, as the wormholes I described in the beginning, where the two asymptotic boundaries are completely separated. But it is still possible to transfer between points on the two S4s by traversing the bulk wormhole without ever crossing the S1. One could thought what would happen if instead of having a disk ADS2, we use the global ADS2 that has two boundaries and the topology of a cylinder. In this case, the AR geometry is again ADS2 crosses 4 crosses 2 cross sigma 2. And the UV asymptotic S4 that we had before is replaced now by an S3 cross S1, and the boundary theories are identified on the common S1. So even with this ansatz, you cannot completely separate the boundaries. Essentially, to separate the boundaries completely, you have to have less supersymmetry, but then you lose control on the geometry. The bubbling wormholes have a codimension 2 locus of conical singularities, the symbol I showed you before, of the form ADS2 crosses 2 crosses 4 in the interior of sigma. And the singularity is located at ZC and corresponds to the fixed point of the Z2 isometry. E1, E2 are the endpoints of the branch cuts. Now, by expanding the metric near the singularity, we can compute the two-dimensional Ricci scalar on the Riemann surface, and we found that is minus pi 4 delta r squared. So we find that we have a conical excess of 2 pi at z critical in sigma along the ADS2 crosses 4 fiber. The Ricci scalar on sigma indicates that the two-cover geometry requires a continuation 2 source of negative tension at Z critical along the fiber ADS2 crosses 2 crosses 4, which means that the dual operator on the S1 conformal boundary must be a source of negative energy. And as we saw, such negative energy, Euclidean energy, is vital in order to construct Euclidean wormhole solutions. Now let me pass to the dual matrix model description of such double cover bubbling wormholes. So we have a two matrix model whose spectral curve describes the two cover bubbling wormhole and is given by this partition function. Now, if we insert two 1/2 BPS Wilson loops that have opposite orientation and they are in the same irreducible representation, these are dual to two disconnected bubbling geometries of a simple type. So their expectation value is given by this expression. And the only effect is that essentially they shifted the center of the Gaussian potential by amount proportional to lambda in its direction. Now one can insert an operator in this background and compute the expectation value. Here we will insert a delta function type of operator, a supersymmetric delta operator of this form. And the effect of this is that it identifies the eigenvalue densities of the two disconnected spectral curves. And the result of this identification coincides with the spectral curve that defines the double cover bubbling wormhole. In terms of eigenvalues, this expectation value can be written in this form. And we can find the finite and saddle point equation for this two matrix model, these being these two. Essentially, they describe two flavor gas of eigenvalues where we have repulsion between XX and YY and attraction between X and Y. Besides the linear force from the Gaussian potential, there is a large external force of order n pulling the X eigenvalues to the right, while an external force of the same magnitude pulls the Y eigenvalues to the left. And an important property of these saddle point equations is that they admit an XY bound state solution when we are at large 't-Hooft coupling lambda. So pictorially, we can see them like this. These are the bound states, and they are stable because we have the repulsion between the similar colored blobs or similar eigenvalues, whereas we have attraction for the opposite. If we had a single Gaussian matrix model with n eigenvalues distributed along a segment L, the distance between two neighboring eigenvalues is delta L over n. So then xi minus xj will be analogous to I minus j times this delta. And from its saddle point equation, we find, as expected also from the linear semicircle solution, that this delta scales as square root of lambda over n, where lambda is the 't-Hooft coupling. Now, for the two-coupled Gaussian matrix model that we are interested here, we have the following pairwise bound state ansatz. So the psi I eigenvalues are smaller than the xi eigenvalues, and they are ordered in this form. For all diagonal I, we have that xi minus psi I is analogous to 1 over kappa, which, as we saw, since these are the columns of the Young diagram, scales as 1 over n. For all ij pairs, where we have I different than j, we have that they scale as I minus j square root of lambda over n, as it was the case also for the single matrix model. Now, if we are further, so these are approximations in order to be able to find the spectral curve. So now we are interested in the semi-classical limit when one is much smaller than the 't-Hooft coupling and the 't-Hooft coupling is much smaller than n. In this case, we have that when I different than j, xi minus psi I is much smaller than xi minus xi j, which is similar to psi I minus psi j. And this means that the characteristic size delta of the bound state, xi minus psi I, is much smaller than the capital delta, which is the distance between neighboring eigenvalues of the same matrix, so xi plus 1 minus xi or psi I plus 1 minus psi I. And in the large lambda limit, the ratio of the delta small over delta large, so the size of the bound state of the distance between eigenvalues at the same I of different matrix models and the ones of the same goes to, once of the same is the capital delta, this ratio goes to 0. Now, moreover, we can approximate the 1 over since xi minus psi I, since this is very small, with 1 over xi minus psi I, which is same order as kappa. And then the previous saddle point equations reducing to this form, where here we have only, we don't have the diagonal part, and they have cancelled with the shift on the Gaussian potential, with the proviso that we have already the bound pairs between for all i's. Now, in the limit of large lambda, the off-diagonal cross terms can be dropped since they are much smaller than the pairs of the eigenvalues of the same matrix model when they are not equal. Now, when this xi minus psi j is very small, we can approximate the 1 over since as 1 over xi minus psi j. While when xi minus psi j is very large, we can approximate 1 over since of this with 0. And the transition between these two regimes happens when the intereigenvalue distance, xi minus psi j, is order 1. Since the width of the bound state eigenvalue distribution is order lambda, any order 1 segment of this distribution, when we are away of the edges, is approximately uniform in this when we are in the large lambda limit. Consequently, when we have a given xi, the 1 over since xi minus psi j terms cancel pairwise within an order 1 neighborhood of xi, because the distribution of psi j is approximately symmetric to the left and to the right of xi in this neighborhood. In this approximation, the off-diagonal cross terms can be neglected when solving the saddle point equations for the bound state configuration. So we end up essentially with these two saddle point equations, which are the same as for the single Gaussian matrix model. And of course, their solutions are linear semicircles, as it was for the one when we had one Wilson loop. So essentially, we end up with two disconnected Wilson loops here, and the only remnant of the present of the bound pair eigenvalues is that the two distributions are overlapping and identifying, recovering the result of the 2-1 map that we have of the double cover bubbling wormhole. An alternative way to see that this density of eigenvalues reproducing the branch cuts and the C-pole poles at 0 and infinity of the double cover bubbling wormhole in the z-plane is by doing the following coordinate transformation. And if we do that, the branch cut between minus square root of lambda and square root of lambda and the C-pole pole at infinity in the x-plane maps to the branch cut at minus C2 to the minus 1 and the simple pole at 0 in the z-plane. And the branch cut minus square root of lambda and the simple pole at infinity in the y-plane maps to the branch cut E1, E2 and the simple pole at infinity in the z-plane. And the density of eigenvalues has this form, which is the same as the harmonic functions for the bubbling wormhole. And this density of eigenvalues can be found from this resolvent, which is the resolvent of the Gaussian-Penner model with this potential. Now, the Gaussian-Penner matrix model, we see it as an effective matrix model description of the double cover bubbling wormhole, whereas the two matrix model, together with this coordinate transformation, is our proposal for how the double cover bubbling wormhole emerges from two Gaussian matrix models via this delta operator that we inserted and identified the eigenvalues. We can do the same for the four cover. So if we have more cuts and more singularities, so more asymptotic these 5 crosses 5 regions that all again are identified on a common S1 on the S4 on their respective S4 boundaries, but I will not show this here. So we can also compute the free energy and the Ocel action from the matrix model and from the gravitational side and compare them. So we can compute the free energy of the delta operator, and to do this we use the saddle point solution we found for the bound state eigenvalue density rho. The background subtraction for the bulk side or the normalization of the dual CFT side is with respect to two decoupled 85 crosses 5. So the leading contribution to the free energy comes essentially from the cross terms, so from this part. And the result to leading order in large n and lambda is this. So essentially the free energy scales as n squared over square root of lambda. Now we want to perform the calculation also from the gravitational side. So a minimal source that backreacts and creates a conical deficit angle of minus 2 pi on the ambient geometry can be modeled by co-dimension 2 cosmic brane of tension 1/2 minus n squared over 2 pi to the 4L8 and the Euclidean action of this form. Now, the cosmic brane is located at the conical singularity, which it is sourcing and is wrapped on the Euclidean ADS 2 crosses 2 crosses 4. And the introduction of the cosmic brane corresponds to the stress tensor of this form, required to cancel the excess delta function in the Ricci curvature. So the on-cell action is this. And likewise, we can find the conical contribution to be exactly the opposite. So at leading order in n squared, the two cancel. So we have to go and study the subleading contribution on the on-cell action of this cosmic brane source and see if it can matches with the matrix model result. So we consider a model where the subleading term in the action of the cosmic brane is given by the Dvali-Gavadadze-Porati term, which essentially is reduced gravity on the bulk source, so this part. And if we do the computation, we find that this scales as eta n squared over square root of lambda. So this scales as the free energy that we found from the matrix model when eta is negative. So the fact that only a subleading order n squared over square root of lambda term survives suggests that the physics of the delta operator could be captured by dynamics that are intrinsic to the bulk source rather than by its tension alone. Now let me make some final comments about this part. So if we take two copies of n equals 4 with the G1 cross G2 symmetry, so in one and the one theory, and consider a general class of correlated observables of this form. So we have the characters of the large representation and some weighting function. Now, if the weighting function is 0, the wormhole saddle breaks the G1 cross G2 symmetry to its diagonal subgroup. If we weight the average with the quadratic Casimir, as was the case of the 2D Young-Mills I showed you before, then what happens is that the connected S1 in the S4 boundaries start disconnecting, and the topology changes to this form. So we can have two asymptotically disconnected boundaries. But and we can find the resolvent from the matrix model, but the problem is that this breaks supersymmetry, so we don't have control from the dual geometry, to develop this idea further. Essentially, one needs to use some less supersymmetric ansatz, and this is very hard. Let me summarize and finish with some future directions. So here we propose the general class of microscopic models of Euclidean wormholes in terms of boundary quantum field theories coupled via higher dimensional topological quantum field theory. These models are reflection positive and do not require any ad hoc averaging over couplings or ensemble of CFTs, and they don't deviate from the usual holographic prescription and rules. There is, though, a resulting sum over a representation of the gauge groups of the boundary theories after we integrate out the messenger theory. This makes the resulting field theoretic correlators to be compatible with what we found when we were computing these correlators in the wormhole saddle. So we have cross correlators with no short distance singularities. We found that similar models can also arise by considering heavy correlated observables in otherwise decoupled quantum field theories. And specifically, we analyzed the case of correlated Wilson loops between two copies of n equals 4 super Young-Mills that they give rise to a bubbling wormhole geometry in type 2B. In the 1/2 BPS case, we have exact control of both sides of the duality, but the boundaries the boundary S4s are connected through an S1, similar to Janus solutions. So they are not completely decoupled. Now, let me give a brief Hilbert space interpretation of such constructions. So we saw in the very, very beginning that the Einstein-Rosen bridge that connects the eternal black hole, the two asymptotic regions of the eternal black hole, corresponds to the thermofield double state. And essentially, we have correlation between the energies of the two subsystems, and their Hilbert space is the Hilbert space of the theory 1 times the Hilbert space of the theory 2. Our proposed models for Euclidean wormholes correlate or entangle UN representations and not energies, as it was the case for the thermophile double. And there are various ways to realize this idea. The first realization was in the presence of gauge constraints coming through the integration out of the topological messenger quantum field theory that was connecting the two boundary holographic quantum field theories. In this case, the Hilbert space reduces to the Hilbert space of theory 1 and 2 with correlated representations, and we sum over these representations. And one could think this in terms of a state of this form. So we have correlated the representations between the two theories. Another way to realize this is to consider assertions of heavy operators that correlate the copies with a similar representation theoretic entanglement. So that was the case of the Wilson loops in large representations in two copies of n equals 4 that we identify with a delta function. A future realization could be that there is some effective constraint on the Hilbert space that can come from a dynamical mechanism that arises in VIR, and this could lead to this cross-confining behavior. So we have the two UN theories of the two boundaries, and they break in the diagonal subgroup. Let me finish with some future directions. The matrix quantum mechanics example that I show you somewhere in the middle, we know that if we have one matrix quantum mechanics model and we include the non-singlet sectors, we can describe a two-dimensional black hole. So it will be interesting, and in that case also there is a sum of representations involved. So it will be interesting to see if these two notions are related and how. It will be interesting to study other top-down constructions that we can embed in critical string theory, and to find less supersymmetric examples, but for which we still have control both on the bulk and the boundary theory, on the gravity and the QFT theory, and study correlated observables such as correlated loops, or extend the idea of this tripartite system. It will be interesting to understand the Lorentzian continuation of this construction, both from the gravity side and from the field theoretic dual. Because okay, here we have the Bankratz examples, but still this could be relevant for cosmology. But we have also constructed different type of wormholes where in the C2 reflection point they have a local maximum, and we saw that this can lead to inflationary cosmology. So it would be interesting to understand those better, and especially their holographic duals, because this could give us an idea for how to formulate holographic description for cosmological space-times. And of course, it will be interesting to study target space Euclidean wormhole background string theory from the Wolzitz perspective. We know for the black hole, the dimensional black hole, for example, there is a Weisum-Witten Coset model description. It will be interesting to see if something similar exists here as well. Thank you.
Okay, let us thank Olga. And questions?
Can I ask the question?
Yes, of course.
Okay. Thank you for the talk. I didn't understand why do we need to couple the two theories with some topological QFT? Is it enough to take two copies, two non-interacting copies of n equals to 4 theory and pretend that they are in the entangled state of thermal field double and they're described by the ADS used to boundaries, no? You need to couple them additionally.
No. So, okay. So thanks for this question. So the thermal field double is an example for Lorentzian wormholes. Here we had the Euclidean ones. In the example of n equals 4, you are right. We don't need the example that I showed here. We don't need to use a topological theory to connect them. We start with two copies of n equals 4. We have two backreacting Wilson loops. And these Wilson loops, they live on the S1 that is identified in the two boundaries. And we compute this, and we find from the matrix model, we find the resolvent of the matrix model that matches with the harmonic functions that give you the metric, the functions of the metric of the bubbling wormhole. So there is no need to use a topological theory to connect them. It's a different example. But another way to get, so the main point here was that we need to get some observable of this form.
Sorry for interrupting, but what is the interpretation on the field theory side? So you kind of construct by hand a non-trivial observable of the in the product of the two non-interacting theories, or you have an entangled state like similar to thermal field double.
It is similar because we have what I mean here by entanglement is correlation between the representations of the two Wilson loops. In principle, these two Wilson loops could be in different representations, but to get the wormhole, you need to have them in this specific state where the representations are the same for the two Wilson loops. So in this sense, it's similar to the thermofield double. And indeed, you don't need a topological theory to connect them. The example with the two boundary quantum field theories connected by a topological field theory that is non-holographic, it is one dimensional higher, is a different example that can give you a similar Zwinger functional.
Do I understand correctly that this is a signal that the two Hilbert spaces, the states of these theories, they kind of entangled? the
Yes,
vacuum state, for example. This is the interpretation of these wormholes.
right.
Okay, thank you. That's what I wanted to understand. Thank you for the talk.
Thank you.
Okay. Going questions once. Going questions twice.
Yeah, maybe I have not a question, kind of not very relevant comment. In principle, you can consider also analogs of Wilson loops in six-dimensional theory, like 2,0 theory, which is dual to ADS7S4. And then you can have also minimal surfaces connecting to spheres, for example. If you consider Wilson surface operator, which kind of related to not as to circle but to sphere. There is a three-dimensional surface like ADS3 and X ending on S2. So then you can also study classical solutions which have, I mean, membrane solutions which connect to S2s. So that will be analog of this Wilson loop for analog of this bridge between two circles, which you discussed, Wilson
I
loop.
see.
Yeah, but then you don't have any gauge theory control over that, but
I see.
formally you can consider this analog.
Okay.
I don't know if this is relevant or not.
It could be, but yeah, I need to read about this. I don't know. I don't have any.
Yeah, there were discussions like, in particular, Drucker et al. And about the one could formally discuss these Wilson surfaces. The Wilson surface operate in six-dimensional conformal theory, which will define conformal defect of dimension 2.
I see.
Which would be like analog of circle or line.
Right.
Yeah, but I don't know if I don't think the membrane solutions are ending on two spheres were discussed.
I see.
I don't know.
Okay. Thank you for this comment. I will check this.
Okay, if there are no more questions, then let's stop here and let's thank the speaker again.
Thank you very much.
Yeah. Thank you for the talk. Okay.